Okay, so in this video, we're going to talk about improper integrals, of which there are two types. So we're going to talk about type 1. These are more obvious integrals because they involve infinity. So type 1 integrals, what are they? They look like this, okay? So I have a typical integral, but within my limits of integration, I have infinity. And I could have infinity in one part of the limits of integration or in both parts. Okay, so let's talk about how to evaluate. So the good news is that I think at this point in calculus, it actually makes a lot of sense in how to evaluate these things. If you think about it, since it involves infinity, you know that we can't do a calculation with infinity, like not directly. So it's going to involve limits. Okay, so here's how you evaluate. If you have some integral of this form, of course it has to be continuous on the interval. So basically, where you have that infinity, you're going to replace that infinity with a variable and then have the variable go to infinity. And this is true for whether you're going to positive or negative infinity. So in this case, I have a similar integral, but now it goes from negative infinity to b. So I just replace where that negative infinity was, but now my limit will go to negative infinity. And then, of course, the question is, what do I do if I have infinity here and here, so for both of my limits of integration? So in this case, what we're going to do is we're going to split the integral up. And so you can split it by choosing some number c. It totally doesn't matter how you split this up. C can be any number, so you can just choose whatever number you think would be convenient to evaluate with that integral. So if it is possible to integrate, then we say that the interval converges. If the integral does not equal some answer L, then we say that it diverges. So it's got to equal a number. As long as it equals a number, then we say that the interval converges. If it is going to infinity or negative infinity, we'll say it diverges. Okay, so let's go ahead and do an example. So I'm going to find the area under the curve y equals 1 over x squared plus 1 from x equals 1 to x equals infinity if possible. So, of course, finding the area under the curve, that is classic integration 101, what we use integration for. So I can set up my integral 1 over x squared plus 1 from 1 to infinity. So what is actually happening here? Like, why should this even work? So a lot of times when we are going to infinity, like you see here, so here's what this little region looks like. So you know at some point, right, the area here, this is an asymptote. And so clearly at some point we are going to just get to a point where this basically bottoms out at 0, but it's not 0. And so that's why these integrals can work. All right, so let's go ahead and let's integrate this. So remember what we said. So basically we have to get rid of this infinity and set up a limit. So I can set up my limit. I've changed this to an a, and now a goes to infinity. And then I just integrate as normal. And so this integral, the antiderivative here is inverse tangent. And then I just set up my limits of integration, and I just have a limit that I have to evaluate here. So then I can just set everything up. So I've got my subtraction all set up. And so from here, so let's actually think about this for a second. So this could be a little bit tricky. I will say that maybe one of the hard things about this is if you don't remember how some of these functions work, as you're going through a lot of these, I would say maybe graph them, like force yourself to look at the graph. You can use a website like desmos.com. So there's usually a handful of classic graphs that we use when we are working with these types of integrals. So if you forgot what inverse tangent looks like, I'll just show you. So what should happen as x goes to infinity? Well, as x goes to infinity, we actually have this asymptote for inverse tangent that just goes towards pi over 2. So this is going to just end up equaling pi over 2 minus pi over 4. But like I said, the hard part about this is if you don't remember how these graphs act, then that can be tricky. So what I would encourage you to do then is just take the time when you're doing your homework to just sketch out what do these different graphs look like. And I would actually force yourself just to draw a rough sketch. If you just look at it on a computer, you're probably not going to remember what it looks like. But if you force yourself just to draw a little sketch, over time you'll probably retain it better. Okay, so so then I'm left with pi over 2 minus pi over 4, so that just equals pi over 4, bada bing, bada boom, we're good to go, we've evaluated the integral. Okay, so now what I want to do is I want to do the same integral, but now I just want to evaluate it from negative infinity to infinity. And so remember, you can split this up using any real number that you want. Now you might say we just used 1, but actually you know what would be way easier to use? It would be 0. So I am going to reevaluate this integral, but I'm plugging in 0 here because in general, right, when I have a limit of integration with 0, oftentimes that just makes it much easier to evaluate. Okay, so now I split this up into 2 separate integrals, and so what I'm going to do now is I'm just going to evaluate this part of the integral right here. So to set this up, so where I had that negative infinity, now I replace it with a variable. So I've got the limit as a approaches negative infinity. So this is all I have to evaluate. And so I strategically chose something that we now know what the graph looks like so we can keep working with it. So this is still going to equal inverse tangent. So now I need to evaluate this from a to 0 and then take the limit. So I can go ahead and set this up. So inverse tangent of 0 minus the limit as a approaches negative infinity of inverse tangent of a. Well, again, you know, we just looked at the graph for this, right? So going to negative infinity, we have this asymptote at negative pi over 2. So again, that's why like drawing and sketching just some of those asymptotes is so helpful, especially if you're rusty, which is normal to be rusty. So anyways, so then my inverse tangent of 0 is 0 minus negative pi over 2, so this just equals pi over 2. So this first integral is just pi over 2. And then, okay, so I have to evaluate this other integral, but the thing is, like, we really did a lot of the work for this already, right? So even though I set up this integral, a lot of this work is just very, very similar, right? So it still equals inverse tangent. Now I'm just evaluating the limit as b goes to positive infinity. My limits of integration have flipped, but, you know, I can just go ahead then and kind of finish the rest of this out. So as we go to positive infinity, I know this will equal pi over 2, and then this is still minus 0, so this just equals pi over 2. So very, very similar. A lot of times evaluating, I know it looks like a lot of work, but a lot of times if you choose, first of all, the right number to kind of break up your integral, doing the second integral will probably take you less time. So then I just add up the two answers. So I've got pi over 2 plus pi over 2, so this is just going to equal pi. Okay, cool. And so that's actually it for this one. So if you want to see more examples, I do have other example videos, or if you have like a request or something, you can always leave me a comment for it. I love it when you guys hit the like button or the subscribe button. And otherwise, I will talk to you guys in another video. Peace.